Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you, is Mars terraforming possible? The reality behind making Mars like Earth. Terraforming is a concept that might sound like science fiction, but it's rooted in real scientific discussions. The term, terraforming, literally means earth shaping, and it describes the process of transforming a hostile, extraterrestrial environment into one that could support human life. Imagine changing the atmosphere, temperature, and ecological systems of a planet until it becomes similar to Earth, so much so that humans could survive there without protective suits or equipment. It's an incredibly ambitious idea, involving complex technologies and massive resources, but one that could offer humanity a way to expand beyond Earth. Now, why is Mars the focus of so much attention when it comes to terraforming? The short answer is that Mars is relatively similar to Earth in a few key ways. At least compared to other planets in our solar system. Mars has a day length close to Earth's, it has seasons, and it even has polar ice caps. However, despite these similarities, Mars is a planet with a harsh environment. Its atmosphere is thin, mostly composed of carbon dioxide, and it lacks the necessary oxygen levels for human breathing. Temperatures on Mars are extreme, with daytime averages around -60 degrees Celsius, and nights dropping much colder. Liquid water, essential for life, as we know it, is scarce and mostly locked in ice. So, when scientists talk about terraforming Mars, they're referring to transforming its landscape, atmosphere, and possibly even its climate, to create an environment where humans could survive and thrive. But how would we begin such a transformation? To answer that, we need to think about what makes Earth habitable: a breathable atmosphere rich in oxygen, a stable climate, and, crucially, liquid water. Creating these on Mars would be a monumental task. It would mean thickening Mars's atmosphere, raising its temperature, and possibly even engineering water systems. Over time, these changes could allow Mars to support not just human life, but plants and even complex ecosystems. But how feasible is this idea? And is it something humanity could realistically achieve? Terraforming, though a captivating vision, remains speculative. Scientists are still exploring whether it would even be possible, let alone practical, to terraform Mars. The challenges are enormous, ranging from technological and resource limitations to ethical and ecological concerns. One major hurdle is Mars's lack of a magnetic field. Unlike Earth, Mars doesn't have a magnetic field to shield it from solar winds, which would strip away any newly created atmosphere over time. Without a magnetic field, any attempt to create an Earth-like atmosphere on Mars could be undone by solar radiation, meaning we'd constantly have to replenish it. Then there's the question of carbon dioxide. Some propose releasing the CO2 trapped in Mars's ice caps and soil to create a greenhouse effect, warming the planet and thickening its atmosphere. However, current research suggests that Mars doesn't have enough CO2 to produce a significant greenhouse effect. Even if we released all available CO2, it might not be enough to warm the planet to levels suitable for human life. Another approach involves using advanced technology to create artificial environments, like biodomes or habitats, rather than transforming the whole planet. These enclosed habitats could provide Earth-like conditions without requiring changes to Mars's global environment. While less ambitious, this approach could be more achievable with today's technology and resources. Terraforming, while it sounds like a giant leap toward human colonization of space, raises deep questions about our responsibilities. Should we attempt to transform Mars, a planet with its own unique characteristics? Are we responsible for any unintended consequences of altering another planet's environment? And finally, what would it mean for future Mars explorers and settlers? Would they be able to fully Earthify Mars? Or would they be living in a hybrid world? One part Earth-like, one part Mars? Terraforming, then, is not just a scientific endeavor, it's an ethical and philosophical one. It challenges us to think about our role in the universe, our relationship with other worlds, and the lengths we're willing to go to secure a future for humanity beyond Earth. As we continue exploring these possibilities, terraforming remains an idea that captivates both scientists and dreamers. The concept may be far from achievable right now, but it's a bold vision that could one day define the future of human civilization in space. So, why is Mars the top choice? When scientists consider the idea of terraforming, one of the biggest reasons is Mars's relative proximity to Earth. Mars is the fourth planet from the Sun, while Earth is the third, making Mars our next-door neighbor in the solar system. This means Mars is more accessible for missions, supply transfers, and potential human travel than planets like Jupiter or Saturn. A round trip to Mars takes roughly 6 to 9 months each way, depending on the planetary alignment, which is feasible with current technology. Another advantage is that Mars has a day length similar to Earth's. A Martian day, known as a sol, is about 24 hours and 39 minutes, just a bit longer than an Earth day. This similarity would make it easier for humans to adapt, since they wouldn't have to adjust to drastically different day-night cycles like they would on other planets. Mars also has seasons due to its tilted axis, similar to Earth. This means that temperature variations and seasonal changes, though extreme, follow a somewhat familiar pattern. This seasonal cycle provides periods when conditions might be slightly more favorable for exploration, and in the long term, could offer a more predictable climate if we manage to alter the atmosphere. A key factor that makes Mars appealing for colonization, and, eventually, terraforming, is the presence of water in the form of ice. Mars has polar ice caps, and there is evidence of ice deposits beneath the surface, while liquid water is rare on Mars due to its low atmospheric pressure. The availability of frozen water is a crucial asset. This water could be harvested and used for drinking, agriculture, and even for producing breathable oxygen and hydrogen fuel. Another reason scientists consider Mars is its gravity. Mars has about 38% of Earth's gravity, meaning it's weaker, but not so weak, that humans would suffer severe health effects. Research suggests that long-term exposure to very low gravity, like the microgravity on the Moon, can lead to significant health issues, including muscle atrophy and bone loss. Mars's gravity is low enough to reduce some health risks associated with space travel, but high enough to maintain bodily functions more effectively than environments with almost no gravity. From a practical perspective, Mars has an atmosphere. Even though it's thin and mostly carbon dioxide, the atmosphere is only about 1% the density of Earth's, but it provides a bit of protection from small meteors and cosmic radiation, compared to the Moon or other airless bodies. Importantly, this existing CO2 atmosphere could theoretically be thickened to create a greenhouse effect, trapping heat and gradually warming the planet, a crucial first step toward making Mars more Earth-like. Mars also holds a special place in human imagination and scientific interest. Since the late 19th century, people have speculated about life on Mars. The famous canals of Mars, though later disproven, inspired generations of thinkers to envision a planet that once supported, or could support, life. This history has motivated scientific exploration, and today, missions continue to search for signs of past or present microbial life on Mars. If microbial life exists or once existed there, it could suggest that Mars already has, or had, some of the chemical conditions needed to sustain life, making it a compelling choice for further study and potential colonization. However, it's worth noting that the conditions on Mars are still extremely harsh by Earth standards. Temperatures can drop to -125 degrees Celsius during winter at the poles. And even at the equator, daytime temperatures can hover around -60 degrees Celsius. The thin atmosphere offers minimal insulation, allowing heat to escape quickly. And Mars has frequent dust storms that can cover the entire planet for days or even weeks. These storms pose a significant challenge for human settlers, blocking sunlight and affecting solar-powered equipment. Mars's lack of a magnetic field is another major obstacle. Earth's magnetic field protects us from harmful solar radiation, but Mars lacks such a field, leaving it vulnerable to the sun's radiation. Without a magnetic shield, even if we manage to build an atmosphere, it could gradually be stripped away by solar winds. This issue complicates the terraforming process and suggests that any attempts to thicken the Martian atmosphere might need ongoing maintenance. Despite these challenges, Mars remains our best candidate for long-term exploration and settlement in the solar system. Its similarities to Earth make it a logical target for future human exploration. And while the challenges are immense, the potential benefits are equally vast. Successfully settling Mars would be a historic step toward making humanity a multi-planetary species, and the lessons learned could pave the way for exploring even more distant worlds. In short, Mars presents a unique blend of challenges and opportunities. While no other planet in our solar system is as close to Earth in both location and potential habitability, Mars still demands a massive leap in technology, investment, and ingenuity. Terraforming Mars may seem like a monumental task, but for scientists and dreamers alike, the idea of transforming the red planet into a new home for humanity remains a captivating and motivating goal. To transform Mars into an Earth-like planet, a monumental number of changes would be required. This process involves altering the atmosphere, climate, and surface conditions so that Mars could support human life, ecosystems, and even agriculture. But what exactly would it take to make Mars habitable? First, one of the most critical requirements is a thicker atmosphere. Currently, Mars's atmosphere is only about 1% as dense as Earth's and consists mostly of carbon dioxide, with only trace amounts of oxygen. For humans to breathe on Mars, we need a breathable atmosphere rich in oxygen. One proposed method is to release the carbon dioxide trapped in Mars's ice caps and underground to create a greenhouse effect, which would thicken the atmosphere and trap more heat, warming the planet. However, research suggests that even if we released all the CO2 available on Mars, it still might not be enough to create a significant greenhouse effect. This means we'd likely need to import or manufacture additional gases, like nitrogen, to create a stable, breathable atmosphere. Some scientists propose releasing fluorine-based compounds, which are powerful greenhouse gases that could help warm Mars faster. These compounds, however, are difficult to produce and might have unknown environmental impacts. Next, we'd need a way to warm the planet. Mars is incredibly cold, with average temperatures around -60 degrees Celsius. Creating a warmer climate would allow liquid water to exist on the surface, which is essential for human life and agriculture. In addition to a greenhouse effect, other approaches might include deploying giant space mirrors to reflect sunlight onto Mars's surface. These mirrors could theoretically focus solar energy on specific areas, gradually raising the temperature. However, this approach would require massive engineering efforts and technology that we currently don't have on a large scale. Another option scientists discuss is nuclear fusion or fission to release heat directly onto the planet's surface or underground. While controversial, these methods could provide a significant boost in temperature. However, the ethical and environmental risks of using nuclear technology on Mars would need to be carefully considered. Water is another essential resource for terraforming. Mars does have water in the form of ice, particularly at its poles and beneath the surface. But this water would need to be melted and redirected to create rivers, lakes, and possibly even oceans. Harvesting this water might involve using geothermal energy or other heating methods to access these ice reserves. Additionally, humans would need to create systems to recycle and purify water to ensure a sustainable supply for any colonies. Another major requirement for making Mars habitable is soil suitable for growing plants. Martian soil, also known as regolith, contains toxic chemicals called perchlorates, which are harmful to humans and most plants. Before plants could grow, we would need to remove these toxic substances or create engineered soil that could support Earth-like crops. Some researchers are exploring the potential of genetically modified plants that could survive in Martian soil, or even help convert it into more fertile ground. This would allow us to grow food and produce oxygen through photosynthesis. Speaking of oxygen, establishing a source of breathable air is crucial. One possible solution involves creating artificial ecosystems, where plants and algae produce oxygen through photosynthesis. NASA has already begun experimenting with a small device called MOXIE on its Mars rovers, which can extract oxygen from Mars's CO2 atmosphere. While this device is small-scale, it demonstrates that generating oxygen on Mars is feasible. For a large-scale colony, we would need extensive facilities, producing oxygen or entirely self-sustaining habitats, like biodomes, where plants generate air. Finally, the lack of a magnetic field on Mars presents a significant obstacle. Earth's magnetic field protects us from harmful solar and cosmic radiation, but Mars lacks such a field, exposing it to intense radiation from the sun. This radiation could damage any atmosphere we create over time, as well as pose serious health risks for humans. Some scientists propose generating an artificial magnetic field, possibly through large satellite systems positioned near Mars. This magnetic shield could potentially deflect solar wind, helping to retain the atmosphere and protect future settlers. However, creating an artificial magnetic field on a planetary scale is far beyond current technology. In addition to these technical requirements, terraforming Mars would require unprecedented resources and energy. Building infrastructure, transporting materials, and deploying technology on such a large scale would demand global cooperation and vast investments. The challenges are immense, and success is far from guaranteed. But for those who dream of making Mars a second home for humanity, these obstacles represent a fascinating puzzle, pushing the boundaries of what we know and what we're capable of achieving. Terraforming Mars is an incredible ambition, but the path is fraught with major challenges that extend beyond technology and engineering. From limited resources to ethical considerations, Let's dive into the most significant obstacles to transforming the red planet. One of the primary challenges is resource availability. Terraforming Mars would require vast amounts of gases, water, and energy to reshape the planet's atmosphere and landscape. While Mars does contain some CO2 in its polar ice caps and soil, as well as water ice, these resources are limited. Research suggests that even if all of Mars's CO2 were released, it still wouldn't be enough to create a thick, breathable atmosphere. That means we'd likely need to import gases, or use advanced technology to manufacture them on Mars itself, a process that would demand tremendous energy and resources. This leads to the next major challenge: energy production. Transforming an entire planet would require continuous, high-power energy sources. Mars receives only about 43% of the sunlight Earth does, so relying solely on solar energy would be challenging, especially during Mars's frequent dust storms, which can last for days or even weeks and block sunlight. Nuclear energy, while powerful, is controversial and comes with significant safety risks. Creating a sustainable, reliable power grid on Mars for such an enormous task is still beyond our current capabilities, and would require new breakthroughs in energy technology. Another enormous hurdle is time. Even with ideal technology, terraforming Mars would likely take hundreds, if not thousands, of years. Raising the planet's temperature, thickening its atmosphere, and creating liquid water sources are processes that take time on a planetary scale. This slow pace makes terraforming a project that would span many human generations, requiring sustained commitment over centuries. It raises questions about whether future generations would continue the work started by their predecessors, especially given the long-term investments and uncertain results. Then there's the issue of radiation. Mars lacks a magnetic field to protect it from cosmic rays and solar radiation, which are harmful to humans, and could pose serious health risks for any settlers. This radiation also threatens any new atmosphere created on Mars, as solar winds could strip it away over time, just as they likely did billions of years ago when Mars lost its own magnetic field. Some scientists propose creating an artificial magnetic field to protect Mars, but we don't yet have the technology to create a planetary-scale magnetic shield. Without this protection, settlers would face radiation hazards, and maintaining a stable atmosphere could become a constant struggle. Soil toxicity is another major problem. Mars's surface contains perchlorates, toxic chemicals that are harmful to humans and most plants. If we wanted to grow food directly in Martian soil, we'd need to detoxify it first. Current research explores ways to treat the soil or create genetically modified plants that could survive in such harsh conditions. This process would require ongoing testing and innovation, adding yet another layer of complexity to terraforming efforts. The psychological and social impacts of living on a partly terraformed Mars also present unique challenges. Living on a distant, largely barren world with limited resources and extreme conditions would be mentally and emotionally taxing for settlers. The sense of isolation and confinement, combined with the harsh environment, could lead to psychological stress. Furthermore, creating a society in such a challenging environment would require addressing social issues, from governance and resource management to conflicts and cultural adaptation. Mars colonists would need to develop new ways of living, which could affect their sense of identity and connection to Earth. And then there's the cost. Terraforming Mars would likely be one of the most expensive projects humanity has ever undertaken. It would require sustained funding from governments, private companies, or even international coalitions. Financing such a vast, long-term project is an enormous challenge, and convincing stakeholders to invest in a project that might not bear fruit for centuries could be even harder. This raises questions about whether humanity is truly prepared for a commitment of this magnitude. Finally, there's the ethical dimension. Altering Mars's environment raises profound questions about our responsibility toward other planets. If microbial life exists or once existed on Mars, do we have the right to potentially disrupt its ecosystem for the sake of human habitation? Even if Mars is lifeless, is it ethical to transform an entire planet? These questions have no easy answers, and are a source of debate among scientists, ethicists, and environmentalists. In short, the challenges of terraforming Mars are vast and complex, involving technical, social, financial, and ethical issues. Overcoming these obstacles would require unprecedented innovation, cooperation, and commitment from humanity. While the goal of making Mars a second Earth is captivating, the path to achieving it would be one of the most difficult journeys we've ever undertaken. Creating an atmosphere on Mars is one of the most challenging steps in terraforming the planet. Mars currently has a very thin atmosphere, about 1% the density of Earth's, which is made up primarily of carbon dioxide. For humans to survive, Mars would need a thicker, oxygen-rich atmosphere to provide breathable air, insulation, and protection from harmful radiation. But how could we create such an atmosphere? One of the most widely discussed methods is releasing the carbon dioxide trapped in Mars's surface and polar ice caps. Mars has CO2 frozen in its polar ice caps and within the soil. By warming these CO2 stores, we could release significant amounts of gas into the atmosphere, creating a greenhouse effect that would trap heat, raise the temperature, and thicken the atmosphere. This warming effect would also make it easier to keep liquid water on the surface. However, research indicates that even if we released all of Mars's CO2 reserves, it might not be enough to create a stable, thick atmosphere. Scientists estimate it would still fall short of the density required for human life. Another idea is to import greenhouse gases from Earth, or produce them on Mars. Some powerful greenhouse gases, like methane or certain fluorine-based compounds, could warm Mars's atmosphere more effectively than CO2 alone. These gases would trap heat more efficiently, potentially creating a more Earth-like climate. However, transporting or manufacturing such gases on a planetary scale would require an enormous amount of energy and resources, raising questions about the feasibility of this approach. Generating oxygen on Mars is another essential step. Currently, Mars's atmosphere contains almost no oxygen, only about 0.13%, compared to 21% on Earth. Scientists are exploring methods to generate oxygen directly on Mars, either through chemical processes or biological systems. One promising approach is to use electrolysis on water, sourced from Mars's ice deposits. By splitting water molecules H2O into hydrogen and oxygen, we could produce oxygen for breathing and potentially for fuel. NASA's MOXIE experiment on the Perseverance rover has successfully demonstrated a small-scale method for producing oxygen from Mars's CO2, proving that oxygen generation is feasible. Scaling up such a system would be challenging, but it's a significant first step toward creating a breathable atmosphere. Some scientists propose using photosynthetic organisms, like algae or bacteria, to help generate oxygen. These organisms could be engineered to survive in harsh Martian conditions, possibly within biodomes or other protected habitats. Through photosynthesis, they would consume CO2 and release oxygen, gradually enriching the atmosphere. Over time, as the Martian environment warms and the atmosphere thickens, more complex plants could potentially be introduced. However, this biological approach would take many decades, or even centuries, to have a noticeable impact on the atmosphere's oxygen levels. Given the vast surface area of Mars, a more radical idea involves creating massive artificial structures, or habitats with controlled atmospheres. Instead of terraforming the entire planet, we could build enclosed, Earth-like habitats, where humans and plants could thrive in a controlled environment. This approach would sidestep the need to transform Mars's atmosphere entirely, focusing instead on localized areas where life could flourish. These habitats could include advanced life support systems to maintain air quality, pressure, and temperature. While this concept doesn't fully Earthify Mars, it's potentially more achievable with current technology and would allow us to settle parts of Mars sooner. The lack of a magnetic field on Mars complicates all of these efforts. Earth's magnetic field protects our atmosphere from being stripped away by solar winds. But Mars lacks this natural shield. Any atmosphere we create on Mars could gradually erode due to solar radiation, as scientists believe happened to Mars's original atmosphere billions of years ago. Some researchers propose deploying a magnetic shield between Mars and the Sun, possibly by positioning a large satellite at a point in space, called the L1 Lagrange point. This artificial magnetic field could help protect Mars's atmosphere, but it's a theoretical solution that would require substantial engineering advancements. In the long term, creating an atmosphere on Mars would require a mix of chemical, biological, and technological solutions. While the challenges are enormous, the potential to transform Mars into a habitable environment remains a driving force for scientists and explorers alike. The road ahead is long and uncertain, but creating an atmosphere on Mars would represent one of humanity's greatest achievements. Water and plants are fundamental to supporting human life and creating sustainable ecosystems, making them essential components in any plan to terraform Mars. But Mars's harsh environment presents unique challenges for water management and agriculture. Let's explore what would be needed to bring water and plant life to Mars. First, let's look at the issue of water. Liquid water is rare on Mars due to its low atmospheric pressure and cold temperatures. But water ice exists in abundance, particularly at the polar caps and beneath the surface. To create a stable water supply, scientists propose melting this ice and redirecting it to designated reservoirs, rivers, and lakes. This would require warming Mars's climate to a point where liquid water could remain on the surface without evaporating or freezing. Techniques to accomplish this include increasing the planet's greenhouse gases, or deploying giant mirrors to reflect sunlight onto specific areas of Mars's surface. Some researchers suggest drilling into underground ice deposits, which are more shielded from temperature fluctuations, by using geothermal energy or solar-powered heating systems. These ice reserves could be melted on-site, providing a steady water supply for any future colonies. However, accessing and distributing this water on a large scale would require advanced infrastructure, including pipes, pumps, and water purification systems to ensure the water is safe for consumption and agricultural use. Next, the question of plant growth comes with its own set of challenges. Mars's soil, known as regolith, contains toxic perchlorates that are harmful to humans and plants. Before crops could be grown directly in Martian soil, these toxic chemicals would need to be removed or neutralized. Scientists are exploring various methods to cleanse the soil, including washing it with water, using specialized bacteria that can break down perchlorates, or treating it chemically. This process would require time and resources, but it's a critical step for using native Martian soil for agriculture. If using Martian soil proves too difficult, importing or creating synthetic soil is another option. By bringing soil from Earth or manufacturing nutrient-rich soil on Mars, we could control the growing conditions more precisely, reducing the risks of contamination and ensuring that crops receive essential nutrients. This soil could be used in enclosed greenhouses or biodomes, where temperature, humidity, and light can be carefully regulated. Greenhouses and controlled habitats are likely to be essential for growing plants on Mars, especially in the early stages of colonization. These structures could protect plants from Mars's low temperatures, radiation, and dust storms, creating Earth-like conditions for agriculture. Advanced greenhouses could be equipped with LED lighting, CO2 control, and water recycling systems, allowing plants to grow year-round. In addition to food production, plants in these habitats would play a critical role in oxygen generation and CO2 absorption, contributing to a more sustainable colony ecosystem. Long-term solutions may involve genetically modified plants that can withstand Martian conditions. Scientists are exploring ways to engineer crops that are more resistant to cold, drought, and low-pressure environments. These plants could be designed to thrive in lower light conditions, and even tolerate the presence of perchlorates in the soil. By developing Martian-adapted crops, we could reduce the need for extensive protective infrastructure, making it easier to grow food directly on Mars. Water recycling will also be essential for Mars agriculture. Since Mars has limited accessible water, every drop would need to be reused as efficiently as possible. Advanced recycling systems could purify water from various sources, including human waste and plant transpiration, to maintain a closed-loop system where water loss is minimized. These systems would ensure that both human settlers and crops have a continuous supply of clean water. In addition to supporting human life, growing plants on Mars would have profound ecological and psychological benefits. Green spaces could provide a sense of normalcy and connection to Earth for settlers, reducing the psychological stress of living on a barren planet. Over time, as Mars's atmosphere becomes more hospitable, plants could be gradually introduced outside of greenhouses, helping to enrich the soil, produce oxygen, and absorb CO2. In summary, cultivating water and plant life on Mars would require innovative solutions in water extraction, soil management, and agricultural technology. With these advances, we could take a crucial step toward creating a sustainable, self-sufficient human presence on Mars. Terraforming Mars would be one of the most resource-intensive projects humanity has ever attempted. Transforming an entire planet requires vast amounts of materials, energy, and time, presenting numerous logistical and economic challenges. Let's dive into the resource-related issues that make Mars terraforming such a formidable task. One of the most pressing issues is the need for raw materials. Mars has limited supplies of essential elements compared to Earth. While Mars's soil contains some useful minerals, it lacks the diversity and abundance of natural resources found on our home planet. Key materials like nitrogen, which is crucial for creating a breathable atmosphere, are scarce on Mars. On Earth, nitrogen is abundant and makes up about 78% of our atmosphere. But on Mars, it's only a trace gas. Without sufficient nitrogen, it would be nearly impossible to create an atmosphere. dense enough for humans and plants to survive. This scarcity means we would need to either import large quantities of nitrogen from Earth, or find alternative methods to create it on Mars. Transporting such massive amounts from Earth is not only expensive, but also highly impractical on a large scale. Each kilogram of material launched into space requires significant fuel and costs, making the import of basic atmospheric components like nitrogen a considerable challenge. Then, there's the issue of carbon dioxide (CO2), which, while more available on Mars than nitrogen, may still be insufficient for terraforming. CO2 is essential for creating a greenhouse effect that could help warm Mars's surface and support plant life. Although Mars has CO2 in its polar ice caps and soil, recent studies suggest that even if we released all available CO2, it might not be enough to create a thick, warm atmosphere. This limitation suggests that we may need additional greenhouse gases, like methane or specially engineered compounds, to achieve the desired warming effect. However, producing or transporting these gases on a planetary scale presents further resource challenges. Energy resources are another major hurdle. Terraforming Mars would require continuous energy inputs over decades, if not centuries. Mars receives less sunlight than Earth due to its greater distance from the Sun, which reduces the potential for solar energy. Additionally, Mars experiences frequent dust storms that can last for weeks and block sunlight, making solar power less reliable. Nuclear energy is a potential solution, but transporting and deploying nuclear reactors on Mars would be highly complex and could pose environmental risks. For sustainable energy on Mars, we might need to consider alternative sources, such as geothermal energy. Though Mars's internal heat is less intense than Earth's, some scientists have proposed using space-based solar power stations, where satellites equipped with solar panels would collect sunlight and beam energy down to Mars. However, this technology is still largely theoretical, and would require massive advancements and resources to implement on a large scale. Water is another critical resource. While Mars has water ice, accessing it and transporting it across the planet would be a significant challenge. Water is essential not only for human survival, but also for agriculture and potential industrial processes on Mars. Harvesting, melting, and purifying water would require robust infrastructure, which itself would consume resources and energy. Since Mars has limited easily accessible water, we would need to employ advanced water recycling and purification systems to maximize every drop. Creating a stable, habitable environment on Mars would also require infrastructure development on an unprecedented scale, from building habitats and transportation networks to constructing life support systems. Every aspect of a Mars colony would demand vast amounts of materials, many of which might not be readily available on Mars. Advanced manufacturing facilities would be needed to produce tools, replacement parts, and construction materials on site. Establishing these facilities would require skilled labor, specialized equipment, and reliable power sources, all of which add to the resource burden. Finally, financial resources represent a daunting challenge. The cost of developing and maintaining a terraforming project on Mars would be astronomical, likely reaching trillions of dollars over the course of many decades. Funding such a long-term project would require sustained investment from governments, private companies, or international coalitions. But given the high costs, political challenges, and slow return on investment, securing consistent funding could be one of the biggest obstacles. In summary, resource constraints, ranging from raw materials and energy to financial investment, make terraforming Mars a formidable endeavor. Overcoming these challenges would require unprecedented innovation and cooperation on a global scale. Terraforming Mars is not just a massive scientific challenge, it's also a test of patience and technological capability. Unlike typical space missions, which might span a few years, transforming an entire planet would require centuries, if not millennia, of continuous effort. Let's explore the time and technological limitations that make Mars terraforming such a long and difficult journey. One of the biggest time-related challenges is the sheer scale of the transformation needed to make Mars habitable. Mars's current environment is vastly different from Earth's. It has a thin atmosphere, extreme cold, and almost no liquid water. Changing these conditions to support life would require a gradual warming of the planet, thickening of the atmosphere, and establishment of ecosystems. These changes are processes that naturally occur over geological timescales, often taking thousands or millions of years. Even with advanced technology accelerating these processes enough to transform Mars within a few human generations is a monumental task. For example, warming Mars's surface alone could take centuries. Some scientists propose methods like increasing CO2 in the atmosphere to create a greenhouse effect. However, even if we could release CO2 efficiently, Mars's distance from the Sun and thin atmosphere mean that the warming process would be slow. Technologies like giant mirrors to reflect sunlight onto the planet's surface could speed things up, but would still require decades of continuous effort. Another factor is atmospheric generation and retention. Creating a breathable atmosphere on Mars, rich in oxygen and nitrogen, is extremely challenging, because Mars has no magnetic field to protect it from solar winds. These solar winds can gradually strip away any atmosphere we create, just as they likely did with Mars's original atmosphere billions of years ago. Developing and maintaining an artificial atmosphere on Mars would require constant replenishment or new methods of atmospheric protection, adding more time and complexity to the project. Technological advancements would also need to evolve alongside the terraforming process. The technologies required for Mars terraforming, like large-scale atmospheric generators, advanced solar mirrors, and protective magnetic fields, are either theoretical or in very early stages of development. Some of the ideas for terraforming Mars are based on concepts that have yet to be proven or scaled up, meaning that even if we start the process, we might need to wait decades or even centuries for the technology to catch up with our goals. Consider the need for energy infrastructure on Mars. Terraforming would require massive and continuous energy inputs, but current energy sources like solar power are limited on Mars, especially during dust storms. Nuclear reactors might provide a more stable energy source, but deploying and maintaining nuclear infrastructure on Mars is an entirely new challenge. We would likely need to develop new energy solutions, such as geothermal or fusion power, which are not yet viable at a planetary scale. Developing these technologies could take decades, slowing down the pace of terraforming. Another major limitation is biological adaptation. For plants and microorganisms to survive on Mars, they would need to adapt to its unique conditions, which include lower gravity, high radiation levels, and limited nutrients in the soil. Developing plants and organisms that can survive and even thrive on Mars could take many generations of genetic engineering and testing. Even then, it would take years for these plants to start significantly impacting the atmosphere or soil quality. The time it takes for ecosystems to establish on Mars is also a limitation. Once we introduce plants and microorganisms, they would need time to grow, spread, and interact with the environment. Ecosystems are complex, interdependent systems that evolve over thousands of years on Earth. And replicating this on Mars would be a slow process. Any significant ecological change on Mars would take hundreds, if not thousands, of years, meaning that humans might not see the full effects of terraforming within a single generation. Finally, human commitment and consistency over time is a challenge. Terraforming Mars would require sustained effort over centuries, involving multiple generations of scientists, engineers, and colonists. Ensuring that each generation remains committed to the project is not guaranteed, as political, economic, and social factors on Earth could shift priorities. Maintaining the necessary resources, funding, and public interest over such a long time frame would require unprecedented global cooperation and dedication. In summary, time and technological limits make Mars terraforming a long and uncertain journey. It would require patience, sustained innovation, and commitment across generations. To make this dream a reality, the slow pace and technical demands are a reminder of the monumental scale of the task at hand. Terraforming Mars isn't just a technical or scientific challenge. It also raises deep ethical and societal questions. Altering the environment of an entire planet impacts not only the natural landscape, but also the potential for life, the philosophy of exploration, and humanity's long-term responsibilities. Let's explore some of the ethical and societal issues that make Mars terraforming a complex and controversial goal. One of the most debated ethical concerns is the possibility of indigenous life on Mars. Although no definitive evidence of life has been found, scientists continue to search for microbial life in Mars's soil and ice. If Mars harbors even the simplest forms of life, would it be ethical to alter its environment? Terraforming would likely disrupt or even eliminate any existing Martian ecosystems, potentially extinguishing native life forms. This raises fundamental questions. Do we have the right to change another world for our own purposes? If life exists on Mars, even in its simplest form, some argue that Mars should be preserved as a natural, untouched environment. Even if Mars is devoid of life, ethical considerations about environmental preservation remain. Mars has its own unique geological and atmospheric characteristics, which have developed over billions of years. Transforming Mars would erase its natural state and replace it with a human-made environment. Many environmental ethicists argue that humanity has a responsibility to respect and preserve the natural features of other planets, just as we strive to protect fragile ecosystems on Earth. By transforming Mars, we might be setting a precedent for how we treat other celestial bodies in the future. Another societal question is who gets to decide how Mars is terraformed and governed. The logistics and funding required for such an endeavor suggest that only a select group of governments or private corporations would have the power to initiate Mars terraforming. This raises concerns about the fairness and inclusivity of such a monumental decision. If a single country or corporation undertakes the project, would they control Mars's resources, environment, and governance? Such a situation could lead to monopolization, inequality, and potential conflicts over Martian resources. The question of ownership and rights also becomes relevant. International treaties, like the Outer Space Treaty of 1967, prohibit any nation from claiming sovereignty over celestial bodies. But these treaties were written before the concept of terraforming. or permanent space colonization was seriously considered. If Mars is transformed into a livable world, would settlers have the right to govern themselves? Or would they be subject to Earth-based authorities? Who would make decisions on the distribution of land, resources, and opportunities on Mars? These questions could lead to complex legal and political disputes, as humans establish a more permanent presence on Mars. From a societal perspective, there's also the question of human impact and responsibility. Once we start transforming Mars, it may become difficult or impossible to reverse the process. The ethical implications of creating a new, human-centric ecosystem on Mars would extend to future generations. Both on Mars and on Earth, terraforming Mars represents a commitment to shaping the environment, and possibly even the evolution of life on another planet. This decision could lock future Martian settlers into a specific environmental trajectory, limiting their ability to adapt Mars in other ways, or explore alternative paths for settlement. Another ethical consideration is the allocation of resources for Mars. Terraforming versus addressing challenges on Earth. Terraforming Mars would require tremendous resources, including funds, technology, and human labor, over potentially centuries. Critics argue that these resources could be better used to solve pressing problems on Earth, such as poverty, climate change, and habitat loss. Investing in Mars might benefit future generations, but it may not address the urgent needs of people on Earth today. This raises the question of whether humanity has a moral obligation to prioritize Earth before dedicating resources to making other planets habitable. Finally, social and psychological effects on Mars. Settlers are an important consideration. Living on a newly terraformed planet would involve psychological and social adjustments, especially for the first generations. These settlers would live in a partially or entirely artificial environment, possibly experiencing isolation from Earth and dealing with the unique pressures of living in a new and challenging environment. Over time, Martian society could evolve in ways distinct from Earth, developing its own cultural identity, values, and norms. How will we ensure that Martian settlers retain a connection to Earth? Or should they be free to forge their own path? What responsibilities would Earth have to these new Martians? In summary, the ethical and societal issues surrounding Mars terraforming involve questions of environmental stewardship, governance, resource allocation, and the psychological well-being of future settlers. As we consider the possibility of transforming Mars, it's essential to weigh these factors carefully, as they have profound implications for humanity's role in the cosmos. One of the most ambitious and vocal advocates for Mars colonization is Elon Musk, the CEO of SpaceX. Musk's vision for Mars isn't just about exploration. It's about establishing a self-sustaining human colony on the Red Planet. He believes that humanity needs a backup planet to ensure our species' survival, especially in the event of a global catastrophe on Earth. His Mars colonization plan is a bold and futuristic vision that has captured global attention and inspired millions. But what does Musk's plan entail, and how realistic is it? Central to Musk's vision is SpaceX's Starship rocket system, a fully reusable spacecraft designed to carry large numbers of passengers and cargo to Mars. Starship represents a new era in space transportation, aiming to reduce the cost of interplanetary travel dramatically. By reusing the rocket, SpaceX can lower costs significantly, making the dream of a Mars colony more financially viable. Starship is designed to carry up to 100 passengers at a time, which is unprecedented in the history of space travel. The ultimate goal is to have fleets of starships transporting people and supplies to Mars, eventually creating a large-scale settlement. Musk has laid out a timeline that aims for the first crewed Mars mission within the next decade. Though this ambitious goal depends on various technical and logistical factors, he envisions a growing colony that could support itself, with resources available on Mars. This concept, known as in situ resource utilization (ISRU), involves using local resources to produce essential supplies like water, oxygen, and even building materials. For instance, water ice found at Mars's poles could be harvested to support human life, while CO2 in the atmosphere could be converted into oxygen or used as rocket fuel. Self-sufficiency is a core aspect of Musk's Mars plan. He envisions a colony that would eventually become independent of Earth, capable of producing its own food, energy, and resources. To achieve this, SpaceX would need to establish infrastructure for agriculture, energy production, and industry. Musk's idea is that over time, the Mars colony would become increasingly self-reliant, reducing its dependence on Earth for supplies. This goal aligns with the concept of a backup civilization, a society that could thrive on Mars, regardless of what happens on Earth. Musk has also outlined plans for terraforming Mars, to make it more hospitable for humans. While he acknowledges that true terraforming may take hundreds or thousands of years, he has suggested nuking Mars's poles to release CO2 trapped in the ice caps, creating a greenhouse effect that could warm the planet. This concept is highly controversial, as it involves the use of nuclear devices, which could have unpredictable and potentially harmful consequences. Many scientists and environmentalists oppose this approach, suggesting that more research is needed before attempting such drastic measures. The technological challenges are immense, and Musk's timeline is considered optimistic by many experts. Space travel involves numerous risks, including exposure to cosmic radiation, technical malfunctions, and the psychological challenges of long-duration missions. Starship, while promising, is still undergoing testing and development. Achieving the level of safety and reliability required for crewed Mars missions is a significant hurdle, and there's still much work to be done to ensure the spacecraft can handle the long journey and harsh conditions of Mars. Despite these challenges, Musk's vision has inspired global interest in Mars exploration and colonization. His bold goals have pushed other space agencies and private companies to innovate, increasing competition and accelerating advancements in space technology. By setting ambitious targets, Musk has brought Mars colonization into mainstream discussion, making it a serious goal rather than a distant science fiction dream. He has also highlighted the importance of making life multiplanetary, a concept that resonates with those who see space exploration as humanity's next great frontier. In summary, Elon Musk's Mars colonization plan is ambitious, visionary, and filled with challenges. Through SpaceX and Starship, he is working to make Mars a viable second home for humanity. While the technical and ethical obstacles are considerable, Musk's vision has inspired a new era of exploration and innovation that could shape humanity's future on Mars. While private companies like SpaceX are gaining attention for their ambitious Mars plans, government space agencies such as NASA, the European Space Agency (ESA), and Roscosmos have long been key players in Mars exploration. These agencies focus on research, technology, development, and international cooperation, gradually building the foundation for a potential human mission to Mars. Their efforts, often slower and more methodical than those of private companies, have laid much of the groundwork for what we know about Mars today. Let's explore the roles of these major space agencies and their contributions toward Mars exploration and, potentially, Mars colonization. NASA, the United States Space Agency, has a comprehensive and long-term plan for Mars exploration, called the Moon to Mars program. NASA's approach is to use the Moon as a testing ground for technologies and systems that would later be applied to Mars. Through the Artemis program, NASA aims to establish a sustainable human presence on the Moon by the 2030s, using it as a stepping stone for deeper space exploration. The agency's goal is to learn how to live and work in a low-gravity, extraterrestrial environment before attempting a Mars mission. By developing and testing systems on the Moon, NASA hopes to reduce the risks associated with a human mission to Mars, which is far more challenging and resource-intensive. One of NASA's major recent projects is the Mars Perseverance rover, which landed on Mars in 2021. Perseverance is equipped with advanced scientific instruments to study Mars's geology, climate, and search for signs of ancient microbial life. It's also testing technologies that could be crucial for human missions. For instance, Perseverance carries a device called MOXIE Mars Oxygen in situ Resource Utilization Experiment, which successfully generates oxygen from Mars's carbon dioxide-rich atmosphere. This small but significant experiment demonstrates the potential for producing breathable air on Mars, a critical step towards self-sustaining human missions. In addition to robotic missions, NASA is working on the Orion spacecraft and the Space Launch System (SLS), designed to carry astronauts beyond low Earth orbit. While initially focused on lunar missions, these systems could eventually support Mars missions. NASA envisions a Mars mission involving a crewed spacecraft that travels to Mars, remains in orbit, and deploys smaller landers to explore the surface. The round-trip journey would likely take 18 to 24 months, including time on the Martian surface. NASA collaborates closely with other space agencies, such as the European Space Agency (ESA). In 2021, ESA and NASA began a partnership to develop the Mars Sample Return (MSR) mission. MSR aims to collect samples from Mars's surface and bring them back to Earth, allowing scientists to study Mars material directly for the first time. This mission would offer unparalleled insights into Mars's history, geology, and potential for life. ESA is also developing technologies for future Mars missions, such as the ExoMars rover, which aims to drill deeper into Mars's surface than any previous mission, to search for microbial life. The European Space Agency (ESA) plays a significant role in Mars research and exploration. Beyond Mars Sample Return, ESA has developed and launched the Mars Express Orbiter and the Trace Gas Orbiter, both of which contribute to understanding Mars's atmosphere, climate, and water history. ESA's approach emphasizes international partnerships, with contributions from countries across Europe and collaborations with NASA and Roscosmos. By sharing resources, knowledge, and technology, ESA hopes to make Mars missions more achievable and cost-effective. In Russia, Roscosmos, the Russian space agency, has a long-standing interest in Mars exploration, although many of its Mars missions faced challenges. Roscosmos partners with ESA on the ExoMars project, contributing the Proton rocket and other hardware. Russian scientists have also conducted extensive research on the effects of long-duration space missions on human health, contributing valuable knowledge for future Mars missions. The China National Space Administration, CNSA, has recently emerged as a significant player in Mars exploration. In 2021, China successfully landed the Tianwen-1 mission, which includes an orbiter, lander, and rover, marking China's first independent mission to Mars. The Tianwen-1 rover, named Zhurong, explores the Martian surface, studying soil composition, atmosphere, and climate. China's success demonstrates the country's growing capabilities in planetary exploration and signals its potential interest in future Mars missions. CNSA has indicated plans for a Mars sample return mission by 2030 and a potential human Mars mission in the coming decades. International collaboration is becoming increasingly important for Mars exploration. The challenges and costs associated with Mars missions are immense, and pooling resources and expertise allows space agencies to achieve goals that might be unattainable alone. These partnerships could play a critical role in overcoming technical, financial, and logistical challenges associated with human Mars exploration. In summary, NASA, ESA, Roscosmos, and CNSA are key players in Mars exploration, each contributing unique expertise and technologies. Their methodical approach and international cooperation lay the groundwork for a possible future where humans set foot on Mars. Establishing a sustainable human presence on Mars will require a range of advanced technologies, many of which are still in development. Future Mars settlers will face unique challenges, from surviving the harsh climate and radiation to generating life-sustaining resources on a barren world. Here are some of the most crucial technological advancements needed to make Mars colonization possible. One of the most essential areas of development is life support and habitat technology. Mars has a thin, unbreathable atmosphere with low levels of oxygen and temperatures that can drop to minus 125 degrees Celsius at night. To survive, Mars settlers will need habitats that provide Earth-like conditions, including stable temperatures, breathable air, and protection from radiation. NASA, SpaceX, and other organizations are exploring habitat designs that could be constructed from materials on Mars, such as regolith Martian soil. Using local materials would reduce the need to transport building supplies from Earth, making Mars colonization more feasible. Radiation protection is another critical requirement. Mars lacks a magnetic field and has only a thin atmosphere, leaving it exposed to harmful cosmic rays and solar radiation. Long-term exposure to this radiation can increase the risk of cancer and other health problems for settlers. One solution involves building habitats partially or entirely underground, where Mars's soil could serve as a natural barrier against radiation. Another approach is to use advanced shielding materials, such as polyethylene or even water, which is effective at blocking radiation. Energy production and storage are also vital for a sustainable Mars colony. Mars receives less sunlight than Earth, and dust storms can obscure sunlight for weeks at a time, making solar power less reliable. Nuclear energy offers a potential solution. Small, portable nuclear reactors, like NASA's Kilopower project, could provide a consistent power supply, unaffected by dust storms. These reactors are designed to be compact and could be transported to Mars as part of early colonization efforts. Other ideas include wind power, which could harness Mars's wind and battery storage systems that could store surplus energy from solar or wind sources for times when sunlight is limited. To create a self-sustaining colony, in situ resource utilization, ISRU technology will be essential. ISRU involves using Martian resources to produce necessities like oxygen, water, and fuel. For instance, water ice on Mars could be extracted, melted, and purified for drinking, and also split into hydrogen and oxygen through electrolysis to produce breathable air and rocket fuel. NASA's Perseverance rover has already demonstrated this concept with the MOXIE experiment, which generates small amounts of oxygen from Mars's CO2 atmosphere. Scaling up these technologies would be a game-changer for Mars colonization, reducing reliance on Earth for resupply missions. Agricultural technology will also play a critical role, since transporting food from Earth would be costly and impractical. Mars settlers will need to grow their own food. Developing methods for Martian agriculture will require advanced greenhouses and possibly genetically modified crops that can thrive in low light and low gravity conditions. Researchers are also studying the possibility of growing food in Martian soil. Although Martian regolith contains toxic perchlorates, scientists are exploring methods to remove or neutralize these compounds, making the soil more suitable for agriculture. Self-sustaining food production would provide settlers with a reliable food source and contribute to mental well-being by creating green spaces on the red planet. Water recycling is another essential technology. With limited accessible water on Mars, settlers will need efficient systems to recycle and purify water. Closed-loop water systems, similar to those used on the International Space Station, would allow Mars colonies to reuse water multiple times, significantly reducing the need for fresh water. Advanced filtration and purification technologies would ensure that water from various sources, including human waste, is made safe for reuse, supporting both human consumption and agriculture. To enable reliable communication between Mars and Earth, high-bandwidth communication networks are being developed. Mars is, on average, 225 million kilometers away from Earth, which introduces a time delay of up to 24 minutes for signals to travel one way. This delay makes real-time communication impossible. However, advances in satellite technology and data compression could improve the efficiency of communication, making it easier for Mars settlers to stay connected with Earth. New satellite networks could also improve communication on Mars itself, providing settlers with reliable, planet-wide coverage for research, emergency response, and daily operations. Finally, transportation and mobility solutions will be crucial. Mars's surface is rocky, dusty, and often difficult to navigate. Specialized rovers and vehicles will be needed to transport people, equipment, and resources across the Martian landscape. These vehicles would need to be robust, capable of operating in low temperatures, and potentially autonomous to assist with tasks in harsh conditions. Innovations in robotics and AI could make it possible for autonomous vehicles to perform tasks like site exploration, resource extraction, and infrastructure construction, supporting settlers and reducing their exposure to dangerous conditions. In summary, the technological advancements needed for Mars colonization range from life support and energy systems to resource utilization, agriculture, and advanced transportation. Developing these technologies will be essential for creating a sustainable human presence on Mars, transforming a distant dream into a reality. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.